Actually, HF is a much weaker acid than the other three hydrohalic acids, which are strong acids. Thus, we use a double less than symbol here to denote that HF is a much weaker acid than HCl. Though HCl is a strong acid, it is weaker than HBr. HBr, in turn, is weaker than HI, which is the strongest acid of them all. Bond polarity therefore plays a minor role in determining the acidity trend. Bond strength and conjugate base stability play larger roles. Let's consider bond strength now. Covalent bonds are strong, but among covalent bonds, some are stronger than others. Bond enthalpy may be used to compare the bond strength of HX. Bond enthalpy is the energy needed to break a covalent bond. The greater the bond enthalpy, the stronger the bond. The table shows the strengths of the various HX bonds. Since HF's bond enthalpy of 562.8 kilojoules per mole is the highest, the HF bond is the strongest covalent bond among the HX molecules. Why? Fluorine, being in period 2, only has two electronic shells. Say we assume fluorine mixes its 2s and 2p atomic orbitals to produce two sp3 hybrid orbitals, then uses one of these hybrid orbitals to form a covalent bond with hydrogen. The overlap of hydrogen's 1s atomic orbital and fluorine's 2sp3 hybridized atomic orbital is pretty good. According to the valence bond theory, which you learned in Chemistry 1, the greater the overlap of atomic orbitals, the more stable the bond, the stronger the bond. Thus, the sigma bond formed is rather strong and bonding electrons are the happiest. Why are they the happiest? It is because they get to be as near to both nuclei as they can possibly get. And why do they like to be near the nuclei? Well, electrons are negatively charged and positively charged protons live in nuclei. The oppositely charged particles, that is, bonding electrons and protons in nuclei, attract. The nearer oppositely charged particles are to each other, the stronger the attraction between them. Both nuclei are also the happiest as they too are attracted to the bonding electrons. Therefore, the rather strong mutual electrostatic forces of attraction between the bonding electrons and nuclei make the HF bond the strongest and the shortest among the HX bonds shown. Now let's consider why the HI bond is the weakest, as evident by it having the lowest bond enthalpy of 298.3 kilojoules per mole. The overlapping of the atomic orbitals of hydrogen and iodine is poorer than that of hydrogen and fluorine. The bonding electrons in HI aren't too near the iodine nucleus. Like fluorine, let's assume iodine carries out sp3 hybridization and uses one of these hybrid orbitals for bond formation. Iodine is in period 5, so it has 5 shells of electrons. Iodine's 5sp3 hybrid orbital, made from 5s and 5p atomic orbitals, is relatively far away from the iodine nucleus. Recall that when the principal quantum number n equals 5, we are dealing with the fifth shell. The bigger the value of n, the farther it is from the nucleus. Thus, this hybrid orbital, 5sp3, is relatively far away from the iodine nucleus. After the long 5sp3 hybrid orbital overlaps with hydrogen's 1s orbital, a long covalent bond is formed. The distance between the bonding electrons and iodine's nucleus is therefore considerable. This arises mostly from the contribution of iodine's long 5sp3 orbital. The long covalent bond between hydrogen and iodine is due to the repulsion between the bonding electrons and iodine's core electrons, that is, the electrons living in the inner first to fourth shells. This repulsion prevents the bonding electrons from being too near the iodine nucleus. This interelectronic repulsion is greater than that between HF's bonding electrons and fluorine's one as co-electrons. Since the bonding electrons are farther away from one of the nuclei, that is, the iodine nucleus, the electrostatic forces of attraction between bonding electrons and nuclei aren't as strong. Thus, HI's long covalent bond isn't as strong as HF's short covalent bond. Thus, the longer the HX bond, the weaker it is, the easier it is for the HX bond to eventually ionize into H plus and X minus. That is, the more acidic HX is. Now let's look at conjugate base stability. How acidic an acid is depends on how willing it is to convert into H plus and its conjugate base. In the case of HX, the conjugate base is X minus. An acid is very willing to ionize only if what it ends up becoming is stable. So if the structure of the conjugate base X minus is highly stable or can be stabilized by a solvent such as water, then HX is a strong acid. If X minus is not too stable, then HX is a weak acid. When the negative charge of the conjugate base X minus can somehow be lowered in magnitude, the conjugate base attains greater stability. We can think of this as stemming from the idea that a species with zero charge is neutral, stable, and happy. Having a negative charge means the species has one extra electron. But generally, this is not as ideal as a species with no charge. The closer a species can get to resembling a species with zero charge, the better off the species. When HX ionizes, H plus and X minus form. All the halide ions are negatively charged. However, they differ in size. Let's compare fluoride and iodide ions. Fluoride, F minus, is the smallest since its valence electrons reside in the second shell. At the other extreme end, iodide, I minus, is the largest as its valence electrons live in the fifth shell. The same negative charge is distributed differently over the surface of each halide ion. Imagine both ions are approximately spherical in shape. The surface area of a sphere is 4 pi r squared, so fluoride with the smallest radius ought to have the smallest surface area. Iodide with the largest radius ought to have the biggest surface area. For fluoride ion, its negative charge is dispersed or spread over a smaller surface area, while for iodide, its negative charge is dispersed or spread over a greater surface area. When a negative charge is allowed to be spread over a larger area, then there is less charge present at any particular area. This is a little like the following situation. Suppose some dreadful smelling natto is crushed into a paste and spread evenly over the top of a small piece of toast. The same amount of crushed natto paste is also spread evenly over the top of a very large piece of toast. You are now asked to take a bite of either the small or large piece of toast. Which would you pick? If you dread the smell of the decomposing bean paste and want to taste as little of it as possible, you'd pick to take a bite from the large piece of toast as the unpleasant spread has been thinly spread over it. Similarly, if an undesirable negative charge is well dispersed or spread thinly over a larger surface area, its charge density, that is, charge per unit area, is smaller. A species with smaller charge density is more stable as its charge is nearer to zero. Hence, iodide ion is the most stable. Fluoride with the greatest charge density is the least stable. Hi therefore looks forward to ionizing in water to become the stable iodide ion and hydrogen ion. HF is quite reluctant to ionize into the less stable fluoride ion and hydrogen ion.